Hello friends, my name is Akshans and welcome to CAD Academy. In this lecture of control system, we are going to discuss the time domain analysis, and we will discuss time domain analysis for first order system and as well as for the second order system. So starting with the first order system, first order system. So the transfer function for first order system is given as, basically the transfer function is what? Laplace transform of output divided by Laplace transform of input. Okay, now the transfer function of first order system is generally given as 1 plus this thing. Okay, now so when we take the inverse Laplace transform of this thing, inverse Laplace transform ILT, so let's rewrite this thing as 1 by tau plus s. I have just multiplied the term that is 1 divided by tau in numerator and as well as in the denominator. So I have got this thing. I can rewrite this thing as 1 divided by tau into 1 by s plus 1 by tau. Okay, so tau is what? Time constant here. I'll tell you the definition of time constant also here. So we know that Laplace transform of e to the power minus at is given as 1 divided by s plus a. Alright, so when we compare these two things, we can say that inverse Laplace transform of this term will be 1 divided by tau, which is a constant term here. Okay, and at the place of a, here we have 1 divided by tau, so we can simply write it as e to the power a, which is 1 divided by tau, so 1 divided by tau times t. Okay, so I think I have made this clear. So what we just have done, like at the place of a we have 1 divided by tau, so I have just written 1 divided by tau at the place of a here. Okay, now this is the general impulse response of a first order system, or we can simply call it as system response. Both are the same things. Okay, now what is tau here? Tau is time constant. Okay, and what is time constant? 0.673 times of the steady state amplitude. I'm writing that as a is what? Steady state amplitude. Okay, so time required to reach the system response to 0.673 times of the steady state amplitude is known as time constant. Okay, like if this is the response of a system and this is the final amplitude, or we can say steady state amplitude, so time at which this is the time axis, so time at which the amplitude becomes 0.673 times of a, that time is called time constant of the system, that is denoted by tau. Alright, now we will move to the second order system. Okay, for the second order system we have general transfer function as omega n square divided by s square plus 2 zeta omega n s plus omega n square. Okay, so where omega n is equal to natural frequency, okay, zeta is what? Damping ratio or coefficient. Okay, so what happens in second order system, we will take general cases like zeta is equal to 0. When zeta is equal to 0, the system is called undamped because the system response is like this. Okay, in undamped system, the amplitude of the response doesn't have any decrement, which means that in the response there will be no term that is exponential decaying. Let's put zeta is equal to 0 in this equation because we are going to focus only on the poles. So in the denominator, we know that from denominator we get poles, and from numerator we get what? Zeros. Okay, for now we are focusing on poles only, so we will put zeta is equal to 0 in this denominator equation. So this equation will become s square and this whole term will be 0. So s square plus omega n square, that will be equal to 0. To get the poles we have to get the value of s. So s will be equal to minus omega n square and under root of the whole thing. So what will happen now? This will be plus minus j omega n. So let's plot the poles location. Okay, so this is what? So this is what? Imaginary axis. This is what? Real axis, which is denoted by generally sigma. So this is plus minus j omega n, which means the poles are plus minus j omega n, which means that poles are lying on the imaginary axis, and this distance is obviously gonna be omega n. So this will be what? Plus j omega n. This will be minus j omega n. So whenever the poles are lying on the imaginary axis, then the system is always gonna be undamped system. Alright, now we are done with the undamped system. Let's take another case where we will have zeta is equal to 1. So let's put the zeta is equal to 1 in this denominator equation. We will get what? S square plus 2 omega ns plus omega n square is equal to 0. Alright, so omega n and omega n, so when we add omega n and omega n, we will get what? 2 omega n, and when we multiply these two, we will get what? Omega n square. So the roots of this equation is gonna be minus omega n and minus omega n. Alright, now let's plot this thing. So these are the poles. These are the poles location when zeta is equal to 1. So when zeta is equal to 1, the poles location are, first pole is here and second pole is also at the same location. So this case is for zeta is equal to 1. Alright, zeta is equal to 1, and this case was for zeta is equal to 0. Now let's take another case. If zeta is between 0 and 1, the poles location are going to be somewhere on this dashed line. Somewhere on this dashed line. Okay, and when zeta is greater than 1, then what will happen? Suppose At zeta is equal to 0, we had poles at this point and at this point. When increasing the value of zeta, poles starts moving here and here. Okay, first pole starts moving here. Simultaneously, the second pole also starts moving in this path. Okay, at the zeta is equal to 1, both poles strike at this point, and when zeta is increased greater than 1, then one pole starts moving in this direction towards the origin, and another pole starts moving in this direction after striking at this point in minus infinity direction. Okay, so pole came from here, and at zeta is equal to 1, both strike at this point, and greater than zeta is equal to 1, one pole started moving in this side, and second pole started moving in this side towards minus infinity direction. Now, this was the response for undamped system. When zeta is equal to 1, we will have a response like this one. Okay, so here we are not getting any damp in this response, but here we are getting a critical damp. Damp means decrement, so we are getting a critical damp here, which means it is a critical damped system. Now, if zeta is between 0 and 1, we get a response like this one. Okay, so it is having a damp, but not as critical damp. It is having a damp, but that damp is between undamped and critical damp, which is called as underdamped. Okay, so, and when zeta is greater than 1, we have a response like this one. Okay, now we will look at some formulas that are required to solve the numerical problems of second order system and as well as for first order system. Okay, so now let's consider a response which is like this one. Okay, and another response which is like okay. So these two are the responses. So these two are the systems of which we are going to take help to understand the formulas. Now, okay, this is the amplitude A, which is the steady state amplitude again, and this is also A, which is the steady state amplitude here. Alright, now these two are the time axis. So first formula that I'm going to write here is delay time. Okay, so what is delay time? Time required to reach 50% of steady state value. Okay, delay time is denoted as TD, 1 plus 0.7 zeta divided by omega n is the formula to calculate TD, and unit is obviously the second. Now the second thing is rise time. So rise time is time required to reach 100% of A. Okay, which means to reach A. Now rise time is denoted by TR, and the formula for rise time is omega d, where omega d is equal to omega n 1 minus zeta square. Okay, where omega n is what? Natural frequency, and this is what? Damping ratio. Alright, now the third formula is peak time. Sorry for the bad handwriting. Now peak time is what? In this response, where we are getting the first peak, this time is called as peak time. Okay, to calculate the peak time, we have a formula that is pi divided by omega d, and omega d is again this thing. Okay, now here you can notice that this is what? First peak. This is what? Second peak. It doesn't matter that it is a negative peak. Now this is third peak, this is fourth, this is fifth, sixth, seventh, and so on. Okay, so now to calculate first peak we have Tp. To calculate second peak, we'll just multiply here 2. Second peak, time required is 2 Tp. For third peak, time required is 3 Tp, and so on. Okay, now another formula, that is peak overshoot. So peak overshoot is denoted by MP, and that is C of Tp. C of T is what? Output expression. Okay, now put T is equal to Tp to get C of Tp. Okay, this thing minus C of infinity. This is the formula of peak overshoot, and this peak overshoot, just put the T is equal to infinity in this output expression. You will get what? This C of infinity, and subtract both the things, you will get what? Peak overshoot. Now another thing is, that is percentage of peak overshoot, that is C of Tp minus C of infinity divided by C of infinity into 100%. Alright, this can also be calculated as e to the power minus zeta pi divided by 1 minus zeta square. Okay, so this completed. Now the next and the last formula is of settling time. Alright, settling time is 3 tau for 5% of tolerance. It is 4 tau for 2% of tolerance, and it is 5 tau for 0% of tolerance. Okay, this is plus minus 2%. Okay, so now in this response, there will be a point where this response is reached inside the range of 5%, tolerance. If we have a 5% of tolerance, then settling time is gonna be 3 times of tau. Okay, when we are considering 2% of tolerance, then if it is 2%, then the settling time is gonna be 4 tau. And when we are considering 0% tolerance, like the response has been already reached at A, then this time is gonna be 5 tau. Okay, and tau is given as 1 divided by zeta omega n seconds. Okay, Now in next lecture we'll see the numericals over these formulas. Until then, take care and don't forget to share the video and please hit the subscribe button. See you in the next video.